Okay, I'm a cosmologist. Yeah, so I see live. It's no longer in Zoom. We've started a new science with these people, Lee, Andrew, and Stu. Andrew's here. He's much more smart than I am, so you can ask him difficult questions instead of me. He's my husband as well. What we have done was to create, for the first time, what we believe is a common language between cosmology and biology, and I mean a mathematical common language that can give a quantitative value for the worth of life. And we can then put these before the worth of the remainder of the universe as cosmologists, dark energy, dark matter, etc., etc. Oh, this is boring. Yeah, so you know the universe has dark energy, dark matter, quantum black holes, galaxies, all kinds of stuff. Well, it doesn't matter really. I don't know why I have that there. We want to understand how the universe began. In order to understand these, which is the job of cosmologists, unfortunately, because it's very difficult to answer, we count the number of different things today. The best, if you're a physicist, I mean a microstate. If you're not a physicist, we're just counting different things. So we know the number in black holes. Oh dear, that doesn't work. Okay, we know the number, how many different things exist in black holes. I hope Saul would be here today, but he's not. He won a Nobel Prize on dark energy, and we know that dark energy dominates the number of different things in the universe in this accounting. And so what I and my friends have decided was that we have so far in cosmology been looking at a universe that looks like this, like a barren moon, not one that includes biology. And one day I woke up and I thought, well, what if biology has more worth, or is more diverse, or is more complex than the dark energy that Saul Perlmutter won the Nobel Prize for? So this is the same thing, so we not counted states. And the assumption that the reason why we have a barren moon and count it is because the planet is very small, the universe is huge, 15 billion light years across, and so it's not going to count. And number 3, there are no laws in biology like we have here, a beautiful standard model Lagrangian, so you cannot count the diversity or microstates in biology. And in comes our good friend Stu, who has a theory based on combinatorial innovation that basically describes the processes that appear in biology, or rule systems in biology, and we can kind of roughly make do with that to count the number of microstates or different things in the biosphere and compare it with the number of different things in the universe. So this is where we were before the work. The cosmos has that many things. Our planet is small. And what we found was rather very surprising, was that using this way of counting what we can use for a law in biology, we got up to a lot more things, or microstates, if you're a physicist, than the entire universe. And this is only counting up to 3.5 billion years ago, because my computer wasn't big enough. The first RNA molecule. So what does this mean? That we found that in a currency that physicists use, cosmologists use, which is the number of microstates, at least in a classical system, we could count the same number in our biosphere, and then 5, okay, and then compare the value with the rest of the universe. And what have we found? One is, well, no longer here, but the rest of the universe has a lot less in this kind of cosmos currency than our biosphere does. And to me, that is a very good argument for what will happen if to the entire universe, if our planet becomes extinct and life no longer exists. We really, the entire universe, not just our corner of the universe, but the entire universe will become poorer. And I think that is it.